In this video, we're going to begin learning about the various control structures you can use in Java. Specifically, we're going to discuss how to use a classic for loop to reduce unneeded repetition in our programs. There are a variety of ways that you can control the execution of code in your programs. Each technique loosely falls into three basic categories: sequential, conditional, and iterative control flow. Most languages, including Java, have a variety of built-in statements called control structures that let you write elegant code. Sequential execution refers to rudimentary top-to-bottom code execution in which the first line of code encountered is the first executed, then the next one, and so on. This is basic execution in which all the code just runs, does not repeat nor branch based upon decision-making of any kind. Conditional execution, often called branching, is when code is conditionally executed based upon a logical check. It's kind of like the programming equivalent of coming to a fork in the road and being forced to make a decision. In Java, conditional logic is normally employed through use of an if-else or switch statement. And finally, iterative execution, often called looping, is when a block of commands is repeatedly executed over and over. You can loop a set or definite number of times, or you can loop indefinitely based upon a logical test or condition that is continually evaluated. In Java, the for and while statements are used to employ iterative control flow, or more simply, looping. Let's discuss the most popular iterative control structure, the for loop. Take a look at this witty cartoon. Looks like the boy is using his savvy to avoid writing "I will not throw paper airplanes in class" time and time again. What you see depicted in this comic is a classic C-style for loop, the mother of all looping structures. This is essentially what a for loop is, a multi-part structure that allows you to repeat code in your programs. For loops allow you to iterate or to do something over and over again. You control the loop through the code you write. Depending upon the needs of your program, you can execute a code block a fixed number of times, or you can loop conditionally based upon whether some logical test evaluates to true or to false. Here's the basic anatomy of a for loop. We start with the for keyword and then three subsections that are placed within parentheses. The first part is called initialization, where variables needed to control the loop are declared and initialized. This is followed by the condition, which is the expression that is continually tested to see whether the loop should continue or not. Lastly, we have the increment-decrement section, the section that is used to increase and decrease the values of variables critical to the loop's execution. Finally, there's the loop body, enclosed in curly braces, where the code that is to be executed over and over again resides. Let's return to the for loop from our comic strip. This loop starts by initializing a variable named count to the value of 1. This is often called the iteration variable. This is followed by a condition which is tested each time before entering the loop. In this case, we will keep looping because count is, in fact, still less than 500. Each time through the loop, the code and the body is executed. In our case, that means printing a message to the console. Lastly, the count variable is increased by 1. And this process continues until the condition evaluates to false. In our case, once count is 501, the first number greater than 500. When you first start using these kinds of loops, it's really helpful to engage in a practice known as tracing. Tracing a loop basically refers to walking through a loop step by step to get a better understanding of how the loop will execute. What's important to understand here is that the initialization of variables occurs only the first time through the loop. From there, the condition is tested, body executed, and variables are incremented, and the process starts anew until the test is no longer true. In other words, until it yields a false result. Tracing simple loops is pretty straightforward, and you might be able to do it in your head. Soon, however, you will run into situations where tracing will be of great benefit to you. It is common to nest loops within your programs. Nesting is basically when one loop is placed within another loop. In these cases, the outer loop contains an inner loop. In these circumstances, the inner loop is executed completely for every iteration of the outer loop that contains it. Nested loops are very powerful, but in the beginning you might find it helpful to trace them manually using a piece of paper. Here's an example of a nested for loop. In this case, we are producing a classic times table up to 9 by 9. The outer loop is a definite loop that executes 9 times for each of the numbers 1 through 9. There's also an inner loop, which itself is executed 9 times. You can think about the rows representing each iteration of the outer loop, and each column as representing each iteration of the inner loop. Notice how the iteration variable I from the outer loop is referenced within the inner loop. This is possible because I is said to be in scope. But what does that mean? What does it mean to be in scope? Scope refers to where a variable can be referenced. For example, a variable you create within a loop can only be referenced within that loop. Similarly, a variable you define in a method can only be used in that method. Simply put, the level at which you define something dictates where it is accessible and can be used. If you have the need to declare a variable that is class level in scope, in other words, that can be used anywhere in the class, you would declare it at the class level. Normally, the declaration is placed at the top of the class, immediately preceding any methods. As you learn more about Java, you will see that there are multiple ways to handle these class level variables. In this example, we are dealing with what's called a class constant, a fixed, unchangeable value that can be accessed anywhere in the class. Notice the special naming convention and that the variable is declared with both the final and static keywords. This means that once initialized, the variable's value is immutable. Put simply, it cannot be changed. Let's take a look at a brief example. Notice how the class constant pi is declared at the top of the class, and how it is in scope when it is used in the getArea method further down the class. This is how to deal with important values that do not change throughout your programs.